So welcome to part 3 of the MLIR tutorial on running basic programs. So in the previous two parts, we have seen basically how to run an MLIR program and also how to feed an input to a program. So basically IO for a program. Now in this one, we are going to basically look at how to run the demo example that was there in Alex's original tutorial. So basically this example basically pass input and output, and then also compare the final result between the is demo 3 and demo 4. So basically if you follow the original tutorial, he introduces a new MLIR program basically in demo 2, and then in demo 3 he lowers it the normal pathway down to LLVM IR. In demo 4 it does the same lowering, but this time he does a bit of optimization. He goes via the affine dialect to do affine passes for optimization, right? So the aim of this part is to basically run both the variants and confirm that the final output is identical. I have set up the previous two parts for us to get to this stage, but you might ask, why do we need to do this, right? Why do I need to compare outputs of the program? And I'll give you an example. So there is an example bug in the MLIR project, in the LLVM project, where for a given input dialect program function, basically what happened is without the affine loop fusion pass, uh, they got some answer, and with that pass, basically the exact same command with just extra pass, they got different answer. And this bug is still being worked on, it's not fully solved. So my point is there can be scenarios where when you go through these different passes, you might end up with some kind of incorrect result just because there's a bug in MLIR or something. Of course, it's not going to happen for this simple example, but the setup that I'm showing today is to ensure that we check for those kind of results. So that's the aim of building to this point. Now, how am I doing this? So if you see my repo, there's a part 3 in the repo. There is a demo2.mlir. So this is identical to the one that Alex has used with a few small modifications. This will be immediately obvious to you from the previous two videos. The first thing is we are taking in inputs this time. In the original, he was using empty. We are taking inputs because we know how to do that now. We are also emitting the C interface like before, right? And the rest of the function is exactly the same. Nothing else has changed here. Everything else is the same. So this is our demo source, MLIR source. Now, if you see my make file, I have some basically one target here, basically to lower and optimize. Of course, sorry, two targets, and these correspond one to one to the code that was there in the scripts in demo 3 and demo 4. So basically, both of these folders have a bash script where he lowers the program pass by pass. So I'm just moving all those passes in one shot. So we are not looking at the intermediate outputs, but the logic is exactly the same. I've taken the same flags in the same order. So what is happening here is we are going to first lower. So this is the case without the optimization. So we're going to lower, and in this case there is no. If you see the difference here is basically these passes are not there. So we have the extra affine loop, maybe these four, right? So we are going from linalg to affine dialect and doing some fusion, tiling, normalization, and then coming out. Right? So that is literally the difference between lower and optimize. The rest of the steps are exactly the same. Of course, there is in the end what we do is we do the same thing we did before. We translate MLIR translate from the final lowest level MLIR to LLVMIR, and then we basically do LLC to compile. And what I'm doing is I'm just calling it two different files. So there's 1.o here, and there is going to be 2.o and 2.MLIR. So just to make it easy for us, both the programs are going to go through the same harness in main.cpp. I'll show that in a moment. And but that's it. So basically, two different makefile targets just to lower down in different ways and compile against the same program. So if I just run this, so I need to export my window. So this is basically gone through both the compilations. So you now have all of these bunch of intermediate files. Um, we can see them. It's the same as before. So I'll go to the main.cpp to show you the harness this time. So what do we do? What are we? So, okay. So some of it is exactly the same like we had before. We have the extern definition. To get to the function, we have our structure definition. The rest of it is basically, I'll show you maybe starting from main, and it'll all make sense. So one of the first things we're doing is setting up a random number generator because we want to initialize data. Previously, we set it to some static values, 1, 2, 3, that sort of thing. Here, we're going to like randomly initialize floats. So I just have a helper function here to create the tensors. So if you see here, it's just a type def to basically go from this memref descriptor float 2 to a simpler usable structure, right? And here we are just doing all the things we did before. We're creating the aligned allocated pointers correctly. We're feeding in sizes and strides and so on. So there's just a helper function to do all of that, to capture all of this, so that this time we create multiple tensors of different shapes, right? So we have our two inputs. So if you go back here to this original tutorial, you will see that basically we have two matrices, 256 cos 512 and 512 cos 1024, and the core thing is we're going to do a matmul followed by a relu, right? That's what we are doing here. And so we're doing the same thing. We're going to create two empty tensors for the moment. We're also creating a result tensor, which will be populated by the MLIR function. Then we're initializing with random values. Again, very, very straightforward things. If I just show what's going on here, we're taking the tensor, we're getting the base pointer, getting the sizes and so on, and then looping over all those elements and just putting in a random float value, generating a random value and feeding into the pointer. So this logic here, this access logic, is basically we're using the sizes, the strides actually, not the strides. So we have two dimensions, and basically because we have the strides already saved, we just index by using the stride for each of those. So once we have done that, that gives us our two input tensors. And if you see here, I'm calling the function as before to do the matrix matmul plus relu. But if you do it, we don't really know if it's right or not, right? Like it's going to be some value because it's all random numbers. So I'm going to just have a simple dummy naive implementation in C++ to do the same logic, right? So this is just to ensure that the numbers are matching, right? And highly unlikely, but just to ensure that MLIR didn't mess up. So what we're doing here is going to be very simple. Taking the two tensors, two matrices, and we're taking the sizes. We're checking that because it's matmul, we're checking that inner dimensions are matching. Then we're creating a new tensor for the result. And this is the most like naive implementation that you can have for matmul. Just loop over each element and basic logic, right? We have an accumulator starts at 0 and we just accumulate the inner multiplication. So one row and one column. So I, J, K, except I and K are the first dimension of the first matrix and the second dimension of the second matrix. So with that, you basically have a very simple logic. And what I've done here is I've just done a fused ReLU because I know like that's the logic. Instead of doing it separately, I'm just checking if the final result is less than 0, and then I'm just setting it to 0. Otherwise, I'm going to store the value back into the final result matrix, C matrix. So you see the set and get functions. So again, helper functions, very straightforward, not very efficient. As you can see, I am getting the base pointer and then I'm just indexing into the array and storing the value or getting the value from. Very straightforward. So this gives us our naive implementation in just in C++. Not going to run fast, that's okay. And then we have our actual implementation from MLIR, the function that is lowered and compiled by LLC. So idea here is we're going to compare. So firstly, we're just doing sanity check. We're printing the output rest tensors, sizes and strides to see if it's all okay. And then we're going to do an actual comparison of the values. Here again, I've taken a bit of an efficiency shortcut. I'm doing a mem compare directly with the pointer address of the result and the reference. And we know the number of bytes, right? We know the number of bytes that are going to be there from the align point, which is going to be first dimension, second dimension, size of float. And we are just doing a byte level comparison, right? The cleaner way to do this would have been like just do a for loop and check element by element. But I was just, this is basic, this is going to be faster. This might be wrong in some cases if your floating points don't exactly match. This can happen with things like nan and so on. So it's not safe, but it worked out for me, right? And if it's 0, that means the two versions match. Otherwise, it's not matching. That's the basic idea here. So I'm just going to run the first main. So this is basically the same main.cpp compiled because if you see here, we just reference this interface my function, and in the make file, when we compile main1, we are basically linking, compiling the 1.o coming from that first version, the lowered, simple lowering version. We are compiling that into this binary. So that's the function that we have access to. So when it says MLIR version matches reference, this is the first version of lowering, and apparently the output has matched our naive implementation. So we are good, right? But the point of this test is to also ensure that the other version matches, right? And this is the optimized version. So that is again compiled into main2. The main harness is exactly the same. It's just that we have the output of this kind of lowering going into the program. So it's as simple as running main2, and you see that in this case also the version reference matches. So we are good. So basically in this part, we just wanted to see the accuracy of the computation and to see if different kinds of lowerings don't result in inconsistent results. In the next part, we will basically start looking at time it takes to run these different versions. See you.